Good morning to everyone. Thank you for attending this presentation. Today I'm going to present on the first part of my research, mainly focusing on ground truthing, and this is mainly for rangeland environment. So this is a project that has a main partner, the CRCSI, which is the Cooperative Research Center for Spatial Information, and with partners from the Commonwealth government and also government agencies and universities. Like we have the Commonwealth Scientific and Industrial Research Organization, the CSIR is a partner. We also have the Landgate, which is a state government department in Western Australia. And we also have the University of New England, and I am from Curtin University. And we have a private partner, which is the Agri-Milner Group, which is a consortium of various agricultural interests, and they have some cattle stations, and they also have some agricultural institutes, some agricultural research institute. Like they have some stake in agricultural research in Western Australia. So the Agri-Milner Group is a very important partner in this research because there are some questions that they posed to industry and also to the research bodies in Australia, like how can we best estimate biomass at rangeland scale. So this leads us to ask this question, like what was their main interest, what was their motivation? So in Western Australia, which is one of the states in Australia, is the biggest in terms of land area, and it encompasses an area of about 2.5 million square kilometers. So that's a huge area, and 87% of this land area is rangelands, and as you can see in the picture there, this is the type of environment that comprises the 87% of Western Australia. So currently, most of these rangeland environments, they are managed by rangeland managers. We have pastoral leases from the Crown government. So rangeland managers have got to be very wise in the way they sustainably manage the properties they are working on. Firstly, they have to optimize grazing, so as to optimize outputs and profits for them, while at the same time they also have to balance a sustainable grazing pressure in order to sustainably manage the land, because it's also part of their lease conditions. So the main thing that they're currently doing in the northern part of Western Australia is that the rangeland farmer normally goes in a helicopter, and from the top of the helicopter they're just checking what is growing where, in which paddocks, where to move the livestock next. But this is not a very reliable estimate because they're looking from top of the helicopter, and sometimes they just drive around and just check, oh, what is growing in paddock A or what is growing in paddock B. But this is not sustainable because they have to really manage the way they move their animals around, because it's also important for them to sustainably manage this land at the same time maximizing their outputs. So there have been models that have been developed for the western part of Australia, but they've been developed mainly in the southern part of Western Australia. And this environment is totally different from up north. In the northern part, we have a tropical environment, but down south, it's more of a Mediterranean climate. So these models have not been calibrated for the rangelands. And this work is a pilot project to see if the current models that are working down south can also be used on a greater extent on the northern rangelands. So the main question is, can we then use remote sensing to estimate forage stocks at different parts in the season? And can the rangeland manager just click at the top of, maybe at the click of a button, and estimate, oh, I have maybe 20 tons of biomass available in paddock B, so it's time to move my livestock there. So this is the overall picture of where we're going to, and if remote sensing works, then it is a huge bonus. So if remote sensing works, then our main question is, how best can we derive a ground truth protocol that measures what the satellite is observing from the ground and the heterogeneous environment that is on the ground. So today, which leads me to the outline of my presentation, and in the introduction I'm just going to talk about how these rangeland farmers currently operate, and also what are the challenges they are facing, and give you also an idea of how heterogeneous this environment is, even at 100 meter by 100 meter area, how quickly the environment and even the land systems are changing. And I also introduce you to the study area, which is in the West Kimberley area of northern Australia, which is a very, very beautiful place with a challenging environment and also very, very magnificent in view. Then the methodology that we tried to use in order to ground truth our sites will be explained in detail, and the results we have obtained so far. And also I'll conclude my talk with a conclusion and also an outlook to the future. So today I'm only going to focus on the ground truthing part, which is feeding into the next stages of this research. And just to give you a brief introduction of what happens at the cattle stations. So they have an operational period from December right up until November. So that's their operational cycle. And rain in the rangelands normally comes through tropical monsoons. And then that period of wet season grazing is between December and April, or sometimes going into early June. So in this good period, the rains are falling down and the grass is green, the livestock is happy, and so is the rangeland manager. But then the monsoons will go off around May, June, and then the critical period of dry season grazing starts. So the farmer has to know how much biomass he has in whatever part of the station, so that as he does his rotations, he's not degrading the land. And at the same time, during that period, there's also mastering that is happening. So you can see this is the period of dry, wet season grazing, where the stuff is generally green. And then this is the period of dry season grazing, like this is close to a water bore, and most of the grass is already gone. And the main thing the manager is now looking at in this part of the period is to check where there is available biomass, so he can be moving his cattle around without degrading this paddock in this instance. So also in that June, July, August period, there is mastering going on, and this is when all the cattle or the livestock which is on the property is taken in different paddocks, and then they select which one is going for export, which one will be taken over to the next season, and which will be culled, so that their business continues to go forward. So in this case, if it has been selected for export, then they go with the road trains to wherever the export market is. So in this case, accurate assessment of forage stock is very, very essential to the rangeland farmer in order to set the stocking limits for his property. But then the problem is there is so much variability within these environments, and as you can see, these are pictures we took during our field campaigns, and there is so much variability that it's difficult to even think of one type of method that you can use to ground truth data, so that you have a reliable estimate when you measure this with what the satellite is measuring from top of the atmosphere. So this is a predominantly grassy type of landscape, but with a bit of bush, the same as here, and this is predominantly dead and green. And you also notice these trends throughout the season, like it's never a period of purely green stuff, it's always a mixture of dead and green material, because the animals will die off in the dry season, and they'll also start to pick in the wet season, and the same with the animals also. And in this case, they're also different. Like in this case, this is predominantly trees in the background and a bit of understory, and this is predominantly also trees and grass. There are also some open plains, so it's a very variable landscape. And the key question is, how then can we derive ground truth measurements that can measure what the satellite is measuring from top of the atmosphere and have reliable biomass estimates to feed into our models? So this is the key question, and I'll introduce you next to our study area, which is about 263,000 hectares in area. So the manager has to measure approximately 263,000 and figure out every day what is happening where. So using a helicopter or even driving around is too laborious, considering that there are also some station activities running at the same time. So the Liveringa station, as I've already said, is in the West Kimberley, and encompasses an area of approximately 70 kilometers by 40 kilometers. So the map you see over there, these are the land systems in color, and these are the different land systems that comprise the station. And this part in white is the mighty Fitzroy River, which is a big river up north, which is feeding into the Indian Ocean. So the classes of these land systems were defined by the Department of Food and Agriculture for Western Australia. And the land system generally is just defined by a pattern of soils, vegetation, or a certain topography within a particular area. So for the case of Liveringa, they have about 11 land systems. And for our sampling sites, which are in black, we had to choose sites which are productivity relevant. Like this landscape over here, yes, the cattle can be moved into here, but then when you talk of productivity, it's mainly characterized by trees. So it's an area that the farmer is not really interested in because there is no much understory. So we try to focus our areas on areas where we have a bit of grass and also these brownish areas, because they are feeding from the river, they are generally open plains and they are very good they have a very good stocking rate. So in this particular instance, we try to also optimize our sampling by at least having a representative number of sites across the station, and for each land system we tried to at least have three sites, and in total we had 19 sites. And the size of our sampling on how we did it was, we had an area of 100 meters by 100 meters set out for those 19 sites, and we just tried to at least get a representative measurements while we were doing the indirect measurements, which were visual estimation, pasture height, and also we took red and near infrared reflectances with this crop circle instrument, and we also took pasture height with a pasture disc meter. And our main measurement method, which gave us a true representative of the biomass we're cutting, was the direct harvesting, which is a bit destructive in nature and time consuming. And considering that this environment is quite unforgivable, sometimes you're sampling in 50-degree heat, and this type of sampling becomes laborious and even tedious to the person who is cutting. So in our case, we had 6 cuts per every 100 meter quadrat, but we also covered for a small number of cuts by doing visual estimates and pasture height and NDVI and photographs, which were taken at every 5 meter interval. So for, let's say for visual estimates, we would have 50 recordings per each site, because we're taking it every 5 meter interval across the transact. And in our case, we're trying then to see, can we then use the rapid estimates versus the true, the true representative measure, which is the cut, to give us a representative biomass estimate per site. So I'll talk more of the quadrat cut, which was our very true measurement. So we're cutting 6 of these per site. So what we'll do is we'll get to a site and find a high biomass cut and a low biomass cut from a range of 0 to 10 or 0 to 5, depending on the grass that was growing there. So for a visual estimate score, this could be as number 10. And then later on it was cut and the material was bagged and weighed. And then later on, because we was from Perth to the study area, it's a 2.5-hour flight, and we're going there for a period of a week. So because we have to come with the plane, we had to also find a way of sub-sampling so that we didn't carry all the stuff we collected in the field back to Perth. So we sub-sampled, and then these are the sub-samples that would come out of it. So we'd have 6 sub-samples per each site, and in this case, we also would separate some into dead and green fractions so that in the end we have a representative total and green biomass per site after converting to kgs per hectare. So for our methodology, we try to use each individual site in a regression, like the measured biomass versus pasture height, or the measured biomass versus the NDVI. But we're not very successful with the linear regression because of the variability in the landscape. So you discover sometimes the NDVI, normally it is a greenness index, so it just works during the wet season when the stuff is green, but in the season, like in the earlier part of the season between February and December and June, the NDVI would not respond because then the stuff is dead. So NDVI could not carry us through the whole sampling period. For pasture height, it was the same. Like you discover in some other sites, pasture height would work very well because you have steady grasses, but the moment you start to have annual grasses, then the grass starts to fall over. So linear regression was not working successfully. And for visual estimates, there was always a bias between the estimators were having two at each go. So we were facing problems like, then how do we get a representative biomass estimate per site? And in the end, we ended up using a multivariate regression approach, where the X variables in this case were all the measured indirect estimates, like visual estimates 1 and 2, because there were 2 people recording, and then the NDVI and also the pasture height. And the length system and also the sampling date as the X variables in the multivariate model. And then our Y variables were green and total biomass, which I've already shown how we calculated. So we were very happy that our multivariate approach was very robust, because in the end, the most significant factors are the ones that I display over here. So we'd run the multivariate model with all the terms, the visual estimates, the NDVI, the pasture height, and then here I displayed 2 or 3 of the most significant terms for a different grouping. So for open plains, visual estimates and NDVI had the most significance. And for bunch grasses, it was pasture height and visual estimates. Why? Because bunch grasses, they are a bit steady, so they can resist the compression of the plate better than the open plains, which were characterized by annual grasses. And for Pindan also, it had this type of wiry type of grass, which also could resist the weight of the plate, and the same for spinifex. So that's why you see pasture height had a greater effect in this point. And our visual estimates, though biased, they were handy, especially in the open plains, where no method was working. And we are good to say that we've managed to find a way of estimating the site biomass. So this was the multivariate regression model. This is the one-to-one line. And we identified a few outliers, and some of them were due to measurement errors or scale errors, and we took them out of the analysis. That's why we had these very good relationships, which I've already shown on the previous slide. So in conclusion, we discovered that no single method was suitable for ground truthing remotely sensed estimates. So in the end, we had to use a combination of methods, and we're also good to report that our multivariate model was very robust enough to at least give us a site biomass estimate. And going forward, my conclusion is that rangeland environments are very complex, and one method is not going to give you the results you require. So a combination of methods or instruments will give you a better estimate. And looking to the future, because we've managed to calculate the site biomass, now we can move on to derive temporal indices to delineate productivity based on the work that we have already done. And thank you very much. I just acknowledge also the sponsors of the project, the CSI, CSIRO, Kettering University, Landgate, the University of New England, and all the partners we have in the fieldwork. And this is a picture of the Kimberleys. It's an area just close to where we're sampling. Thank you very much.
Thank you for your presentation, Charity. I think we've got enough time for one good question.
It was a really good presentation, thanks for that. I lost the start of your presentation, though. You might have already mentioned that. What kind of satellite data did you use? And why did you choose NDVI instead of a different vegetation techniques?
I also mentioned that in this case, this is the ground truthing stage of the work. So later on, this is where we're going to use vegetation indices. What we needed to do was to get a representative site average of biomass, because with 6 quadrat parts that we're cutting per site, they were not robust enough to just get an average of 6 cuts. So the indirect methods we're doing were then covering up for the less cuts we're doing. So this was just to get a biomass estimate, and later on then use it to derive vegetation indices using satellite images like Landsat and models. But the NDVI was just it's an on-ground sensor which we used for ground truthing, and later on we'll use that also maybe to compare with a Landsat NDVI or something like that.
How do you account for the tree biomass? What kind of ground truthing data?
In this case, further on as we're going, like like in this case, because our sites they're not treated as such, so we're able to get away with just our estimates as they are. But further, if we're now going to then use the estimated biomass we have precise to the station levels, then the trees will start to come in, and already we've started to develop a mask for this work when we start doing the vegetation indices. But currently we're just using almost sites which are treeless.
I'd like to thank Jyoti again for her presentation. And I'd like to thank all the presenters and everybody for coming for this technical session. And we'll start with Vegetation 2 after the lunch break.